Was that, what's that? Was it okay? All right. I'll talk about the solution to this maybe next class. Let's start with today's material. We are starting 2.6, which is titled Implicit Differentiation. And I believe there was a short 6-minute video on this. Maybe not. And this section is critically important for the next section that we're going to do, which is 2.7, which is entitled Related Rates, which is arguably one of the top 3 most difficult things we'll do in this class, if not the top. Most students will say it's right up there. There's maybe 1 or 2 other things that we will do that students struggle with, but 2.7 is usually the biggest challenge because it's word problems. And to do the word problems, you have to be able to do this, what we're going to do today. All right? So we kind of need to, you know how when we were doing the limit and then I gave you the shortcut rules, you know, what you were just quizzed over, we kind of got to like take off the limit goggles and put on a different pair of goggles and look at derivatives in a different sort of, from a different perspective. Implicit differentiation is kind of looking at derivatives again from a slightly different perspective. And so if it feels like we're starting something new, it's kind of because we are, all right? But there's a lot of things still connected. So what I want to first start with is just reminding you that when we had a function, right, y is a function of x, that if we pick a point, we can find the slope of the tangent line. The slope of that tangent line will be equal to the derivative there, right, y prime. But in Leibniz notation, we would write dy dx. And here we're saying that x is here and y is here, right? You remember that notation? We'll be using that notation exclusively today and exclusively in 2.7. And hopefully you'll see why Leibniz notation is better suited for what we're about to do, all right? So when you look at the slope of the tangent line, where it all came from was this idea of having a point, fixing it, and then taking a different point and trying to construct a triangle through there and finding the slope of that we call the secant line. And then we move that point closer to that point, right? And then eventually put it right on top. And that's how we got the derivative, right? We took a limit. But if you look at this little triangle, before we move the point, this is always the change in x, delta x, that's the change in x. This is the change in y. So slope is defined to be rise over run. We take that ratio, delta y over delta x, that gives us the slope of this purple line. We take the limit, that moves the point on top of the other point, and that's where we get this notation, dy dx. So dy dx implies that a limit has been taken. Now, what I want you to understand before we proceed is that when we look at this function, x was called the independent variable and y was called the dependent variable. Meaning that if somebody provided you a value of x, you could determine what y was and then go figure out the height of the function there, right? So the y value depended on the x that was being plugged into the function, right? Everyone clear on that? X is independent, y is dependent. And when you write this ratio out, change in y over change in x, what we really didn't talk too much about is how much is this x changing by? Because the answer, right, our answer is the ratio of the change in y over the change in x. But how much is just the x changing by? And what I want you to kind of visualize is that that's always changing by 1 unit length. Okay, so just imagine that dx is a 1. If that dx is a 1, then your change in y over change in x is really just your change in y. Does that make sense? If this is 1, then dy is just, then the slope of the tangent line is just your change in y. So imagine, if you will, that we have a clock, okay? We're going to start a clock, and we're going to start moving our x value along the x-axis, right? And as we move it, it draws the function, doesn't it? Okay. The rate at which we're moving the rate, remember rate is a derivative. The rate at which we're moving the x is 1. So it's a constant. It might be 1 inch per second, 1 mile per second, 1 mile per hour. But everything that we've done, I want you to imagine that the x value is changing at a constant rate. So it's not like slowing down, speeding up, slowing down, speeding up. It's just moving along the x-axis. And as we move, the y value changes, doesn't it? And that change is our derivative. Okay. I know this is slightly confusing because you're like, and so what's the big deal, right? Let's just hang on and go for the ride, all right? Always leave that darn mouse over there. All right, explicit versus implicit equations. So what is an explicit equation? What is an implicit equation? Well, an explicit equation is any equation where you can solve for one of the variables, and it does not matter which variable you solve for. Okay? So look at the first three here. All of these equations have been solved for one of the variables in the equation, right? The first one solved for y, the second one solved for y, the third one is solved for x. So in the first two, I could write something like this: y equals a function of x, which is 3x plus 1. This implies saying that y is a function of x means that x is the independent variable, y depends on x, right? Y depends on x, because it's solved for y. Yes? Did someone say something? Oh, he was talking. The second one, same thing, right? Y is equal, I can call it f again, but I'll call it g, is square root of sine x. And then the last one is also an explicit equation, but it's not solved for y, right? It's solved for x. So I could write something like this. X equals, let's use a different letter, h of, now I wouldn't say x, I'd say what? H of y, and that would be y cubed plus y, and that's it, right? So y depends on x depends on x depends on y, yes? Now if I ask you to take the derivative of this first one, we should all be able to do that, right? The first one, no problem. The derivative of y is 3. The second one, well, that's going to be a little more involved because it's some chain rule. So we get some like 1 over 2 root sine x times cosine x, something like that, right? And then how about this third one? What could you ask for here? Not y prime, you would x prime. X prime would be 3y squared plus 1, right? Does that make sense that that's what would happen? If you have an explicit equation, these are the results that you get. It's just this derivative, it's what we've been doing, there's nothing new. Now there is a little bit that we need to discuss as far as this notation. On this first one right here, I'm out of room over here, let me put that over here. I could write this a different way. I could write that in Leibniz notation, it would be written dy dx equals 3, right? And when you look at this Leibniz notation now, what I want you to recognize is that the variable up here, y, is the dependent variable, and the variable on the bottom is the independent variable, right? Same with this one. I would write dy dx equals 1 over 2 root sine x times cosine x, right? But what would I write here using Leibniz? D what? dx dy. And that would be 3y squared plus 1. And the reason I write dx dy instead of dy dx is because this variable should be the dependent variable and the variable on the bottom should be the independent variable. And since y was the independent, and x depended on that, right? Then we flip it over.
Just to clarify on the top where you put dy over dx equals 3, the top is the dependent?
Dependent over independent. Now, listen to the way I say this. For this problem right here, okay, for this equation or this function, I took the derivative of this with respect to x. When I say with respect to x, what I mean is x is the independent variable. Here I took the derivative with respect to x because I was treating x as the independent variable. Here I took the derivative with respect to y because y was the independent variable. So when we say with respect to x or with respect to y, then we're saying that that variable, whatever we say, x or y, is the independent one. We still all okay with this? Now, it's really nice when we can solve an equation for one of the variables, because then the derivatives are pretty straightforward. If you can solve it for y, it's just this. If you solve it for x, it's just this. Nothing real, no big change, right, other than the flipping here? Okay. But what if you have an equation that you cannot solve for x or y? Those types of equations are what this is about today. It's about equations where you cannot isolate variables, and these are called implicit equations. And I gave you just 3 examples. Now the first one, x squared plus y squared equals 16. In my notes I explain what that is, right? Oh, I don't need to write it down. It's right there. Oops, there we go. This is a circle. Do you all recognize that as a circle? Yeah. I hope so. There's a general equation for circles that you should all know. This is the equation of a circle that's centered at HK. So if you draw a circle and you put the center here at HK and you draw it with a radius, a radius of r, that's the equation of it. Now if you put this circle at the origin, right, the center is 0, 0, then that 0 just becomes x squared plus y squared equals whatever r is squared. So please keep that in mind. It's there. You may need that at some point. Now, when you look at this circle, the first thing that should come to your mind is that this is not a function, right? It fails the vertical line test. And that's a big deal because everything we've done up to this point has required that you could write it as a function. And we've pretty much exclusively looked at functions of x, right? f of x equals, or y equals something with x's in it. So y depended on x, y was a function of x. So everything we've done has always passed the vertical line test until now. Now we have something, it's a curve, it's defined by that equation. It has tangent lines. I mean, you can pick any point on this circle, right? And you can imagine that there is a tangent line that goes to that, on that point. So it looks like if I choose my x value here to be 2, I know that's hard to see, but if my x is 2, I do have a tangent line, don't I? But there's another one down here, because there's another point that corresponds to 2, right? This is 2 something, question mark. This is 2, and then the y coordinate is something else, right? And so if x is 2, I get 2 tangent lines. So if I tell you right now, hey, give me the slope of the tangent line at x equals 2, that's not enough information for you, is it? You not only need to know the x coordinate, but you also would need to know the y coordinate so you know which of these 2 points I'm talking about, right? So geometrically, we know that the tangent lines exist. The question is, how do we find them? We need a derivative, right? But all the derivatives we've ever done, we've been able to solve for x or solve for y. Well, mostly solve for y, but we saw in the previous little example you could solve for x. So if I take this equation right now and ask you to solve for y, could you? Yeah, you actually could solve this for y. It would take a little bit of algebra, but you could do it. So let's just try it real quick and see what would happen. If If we solve this for y, I would first isolate my y squared by subtracting x squared on both sides. Then I would come in and take the square root on both sides, right? And anytime you come in and you take the square root, right? If you initiate the square root yourself, you have to do plus or minus. Okay? That's the rule. So I have to put plus or minus here. The left side will be y, the right side is plus or minus root 16 minus x squared. And now what I am saying is that y depends on x, right? However, I'm going to get two different answers. For each x value I plug in, I have a positive and a negative answer. So this no longer qualifies as a function. One input gives you two outputs, and that's no good. But I still do have a relationship here with y and x, don't I? So what I could continue to do is break this up into two different functions. I could say, all right, well, y is positive. Here's the positive one. And I could say that y is also the negative one. And if you look at these by themselves, right, if I just handed that to you, that was on the quiz. If that was on the quiz, then I asked you to take derivative, you could do that, right? This one, same thing, you could do the derivative. So we could get answers for each of these, and then we could go and get slopes of tangent lines and be done. But it required a little work to get y. Understand? I'm not going to take derivatives of this, because that's not the point of today. So let's look at the second equation. Can you solve for y here? I heard no. Why not? Yeah, you can't isolate it. So you might get clever and you might be like, okay, yes I can. I can isolate it here. Watch. There it is, right? Its cosine of y is that. And then I could come in and bring the arc cosine in on both sides. Bring inverse cosine. So take arc cosine of this side and take arc cosine of this side. Ah. Right? And on the left side you get what? Y. And then this thing over here, right? Right there. The problem is that in order to know what y is, it's not dependent on just x. It depends on what? X and y. So think about that. To know what y is, you need to know what y is. And that is not going to happen. Right? So the first problem I gave you with the circle, it was possible to get y by itself, and we could then still go and get derivatives. This one, however, we cannot. And this one, you just trust me, you couldn't do it on that one either. So maybe that means that these, maybe they don't have tangent lines. I don't know. Well, would you like to see the graph of those so I can convince you they have tangent lines? All right, so look, this equation, remember, any equation that has x and y in it means that you just need to find x's and y's that make it true, right? If I write x plus y is 4, you just have to give me an x and a y to make it true. So like 0 and 4 work, 4 and 0 work, 2 and 2, 3 and 1, 1 and 3. We go all day long, right? We graph this, it would be a line. Now, are there x's and y's that make this one true? I don't know. I'm going to ask the computer to tell me. All right, so let's look at that one. There's the circle. Let me hide that one. And this one. You ready? Here it comes. There it is. That's the graph. Yeah, sideways, right?
Wait, that's the graph?
That's the graph of that equation. So if you find x's and y's that work, right? These are all of the x's and y's that work. So this point right here, if I knew its x and y coordinate, which I don't, and I plug that x in and that y in, I would get it. This equation would be true. All right, so there are x's and y's that make it true. So there is a graph, there is a curve created by all those points. And I think I hope it's obvious that if you have a point on this curve, that there is a tangent line there. And the question is, can we find the slope of that tangent line? Right? And this goes for any point. Now, is this curve a function of x? Fails the vertical line test. So this is just like the circle. We have vertical lines that would hit it in more than one place. It is not a true function. But it's obvious that there are slopes of tangent lines all over it. We need to be able to find those. So I haven't shown you how.
So just because it's not a function, it will still have tangent lines? So
Just because you don't have a function of x or a function of y, you should be able to find slopes of tangent lines using what's called implicit differentiation, which I am going to show you. Pardon me?
Can't give it a range or something.
Like break it up?
Yeah.
Is that what you mean? Like we did with the circle? Like break it into two functions?
Yeah.
Well,
Like that function, but then give it a range or whatever.
yeah, well, it's easy on this one to see how we did it because we square rooted and we got two different functions. And actually those two functions we had, this one right here and this one, if you graph these, okay, if you graph this one, what it does is draws the top half of the circle. You graph that one, it draws the bottom half. But you will not be able to do that for this one. There's no way you'll be able to break it up to just draw like part of it and then part of it. Not easily. I don't see a way we could do it. All right. And then this last one, I just want to show you the picture of this last one, okay? Because the picture of this last one is pretty interesting. All right. I keep on thinking this is my mouse, so I'm going to put that over there. All right. Let me hide this one. Ready? This one's really interesting. That's really weird, right? This is definitely not a function of x. I mean, you can pick some points here. I don't know. That doesn't quite make it, but I mean, here it looks like there's like, if you pick 3 for x, right? Looks like there's 1, 2, 3, 4 different y values, right? That would make that work. And that means there's 4 different tangent lines that you could get. So again, this goes back to the idea of that circle. We know that there were 2 tangent lines on that circle, right? But I couldn't just give you the x if I wanted to know the slope of the tangent line. I'd have to give you the x and the y. And then the same thing goes for here. If I wanted to know the slope of the tangent line here or there or there or there, to know those slopes, I would have to provide you the x and the y. And then you could give me an answer, right? All right. All right, you ready to see how how implicit differentiation works? Let's do it. I'm going to get a blank sheet here. Where the hell is it? There it is. All right, let's start with this first example. All right, what I'm going to ask here first is for us to find y prime, which we know from our notation meant dy dx, right? I want to know the rate at which y is changing with respect to x, right? That's what I want. Now, one last little thing here. When we were talking about the notations for derivatives way back when, like, okay, hey, y prime means this, 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 there was a notation that said this. You could write d over dx, and then here you could put the function f right there, and that this was the same as y prime. In other words, I'm taking the derivative with respect to x of some function, all right? So when you write d over dx, look at it as it's telling you you're taking the derivative with respect to x, treating x like the independent variable of something, in this case f. All right, so implicit differentiation. Here's what you'll do. You will look at the equation, you'll write it down, and we're going to do something we've done with the equations our entire lives. We've always liked to add things to both sides, subtract things, multiply, divide, right? Square both sides, square root both sides. We're actually going to take the derivative on both sides of the equation. We're going to take the derivative on the left side, and we're going to take the derivative on the right side. But we're going to take the derivative with respect to what variable? Yx. That's right, because when I told you what I wanted you to find, right? I told you to find this, and that meant that I wanted you to treat x as if it was independent and treat y as if it was dependent. Yes? Okay, so I'm going to write down now, let you know what I'm doing, the derivative with respect to x of the entire left side must equal the derivative with respect to x of the entire right side. Do you understand the notation? This is implicit differentiation. This is what it is. You're taking the derivative on both sides of the equation with respect to whatever variable you need to do. Now, when I take the derivative over here, I'm taking the derivative of a sum. If I have a sum, I can split it into two derivatives, right? That's a rule. So this is the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And that must equal, well, we can do this one, I think, right now. What's the derivative of the constant 16? 0. The derivative of a constant will always be 0, won't it? Because remember what you're saying. When you say take the derivative with respect to x of 16, you're saying at what rate is 16 changing as x changes? Well, 16 never changes, right? So the rate of change is 0. And that would go for any number, any fixed number. Okay, what about this one right here? What is the derivative with respect to x of x squared? 2x, just what you always thought it was, right? I mean, there's no magic happening here, all right? It's 2x. But I want us to pay attention to something. If we do 2x, that would be me applying the power rule to x squared, right? Remember last class we had chain rule? And the chain rule works like this. If I had something to a power, like let's say I had a box or my hand or whatever it is that you don't like, a towel, to the n power, and I took the derivative, right? Then what you do is you would say n comes out, I would take that box, I'd raise it to the n minus 1, right? Yeah. Then you'd say times the derivative of what was in the box. And in this case, I don't know what's in the box, so I'll just put the box and put a little prime mark on it. Make sense? This is the chain rule. Yeah? Yeah. When I just did this, I want you to look at that x down here as being the box. All right? So I did 2 came out, right? 2 times x. Now chain rule times the derivative of what's inside of it. What's inside? X. So watch what I'm about to write. I'm taking the derivative of x with respect to x. Right? With respect to x, I'm taking the derivative of what's inside x with respect to x. And what do you think that is? 1. Now, we didn't have to write that, did we? But I want you to understand that's what we actually did. We did take the derivative of the inside. We did do that. This piece here, right? When this was x squared, this was 2x, and then we took the derivative of x, with respect to x, and it was 1. Questions? Plus. All right? What is the derivative with respect to x of y squared? So now y is the box, right? So 2 drops out, 2y, chain rule, times, now this is the critical thing, all right? We're now taking derivative of y with respect to x. And so I'm going to write that down. I'm taking derivative of y with respect to x. That is not 1. That is not 1. That is, in fact, what I'm trying to find, right? That's what I'm asked to actually figure out. And it just appeared. That's good, right? It's like, hey, I'm trying to find some, I'm not going to make an analogy because I suck at those. All right. All right, so there's where we are, right? Equals 0. Continue writing the equation. And now, I'm gonna rewrite it one more time. That dx over dx, it's really a 1, right? So I'm just going to replace it with the 1 and just write 2x. 2x plus 2y times dy dx must equal 0. And I'm trying to find what dy dx is. And there it is. So now I'm just going to do some algebra, solve for dy dx, or isolate it, get it by itself on one side of the equation. So I'm going to move the 2x to the other side. That'll become 2y times dy dx equals negative 2x, right? Divide by 2y. And you get dy dx is negative x divided by y. And you might look at that right now and say to yourself, wait a minute, hold on. You're telling me the derivative of this thing has x's and y's in it? And my answer is yes, that's what we said would happen, right? This is a circle. We said that if I just give you the x, it's not enough. Well, look, the formula that we have for the slope of the tangent line requires both an x and a y, which is good, right? That's a good thing. So let's talk about this. Let's actually see if this works. Let's pick a point on this circle that we know exists and will be easy to plug in. I'm going to pick the first one, okay? How about this one right here? That point on the top of the circle, isn't that the point 0, 4? Because the radius of the circle was 4 squared, 16, right? So the radius was 4. That point exists. What's the slope of the tangent line there, just geometrically looking at it? Should be 0, right? So when I plug in 0 for x and 4 for y into this formula, I better get 0. Do I? Negative x is 0 and y is 4, and so we get 0. That matches, right? What if I pick this point down here? 0, negative 4. It's still going to be 0, right? And that matches with that. What about this point right here? What's the slope of the tangent line there? Careful, slope of tangent line here is 0, right? This is a negative slope, and then what happens? Whoa, it tries to become vertical. And vertical lines have undefined slopes. Division by 0. And guess what? Our derivative is going to show us that too, right? If I try and plug in this point, 4, 0, into this, I get that the derivative is, what is it, negative x, so negative 4 over 0, undefined.
Is that why on the graph that you showed, it had openings there? It looked like it had openings.
On the circle? No, there should be no openings on it, no. Because the graph doesn't have the tangent lines on it. So keep in mind, this was the derivative for that one. This was the derivative for that one, right? So you can see that it's matching up pretty good. Pardon me? What if you know the x but you don't know the y? Yeah, let's try it. Okay, do you agree, like I could pick 2 here, right, for x? Well, just plug 2 in here, all right? Let's see what happens. 2 here is what? 4. Subtract 4 from both sides and you get what? 12. So you get y squared equals 12, and then take the root 12, plus or minus, right? So let's try 2. This is the point right here, 2. And then the one on top is the positive root 12, right? The slope of the tangent line at this point is going to be what? Negative 2 over root 12. That's the slope of the tangent line there. And it's negative, isn't it? And it looks like it is going to be negative. And guess what? If you go out to 45 degrees right here, the slope of the tangent line there is negative 1. But you'd have to know what that point is. It's not 2, 2. You have to figure it out. Anyone know how they could figure out what that is? There's a couple of different ways. You could use some trig functions, but you could also just use some common sense. Look, if I don't mean that in a bad way. I don't mean that in a bad way. I'm sorry. That sounded rude. if you're at 45 degrees, your x and your y values are the same, aren't they?
Yeah.
So I could just rewrite that equation and make them both x's, right? Like x squared plus x squared, because x and y are identical at that 45 degrees, equals 16. That's 2x squared equals 16. That's x squared is 8, and that means x is root 8. So, well, plus or minus, but. So if I go out root 8, up root 8, I will be where I need to be, right? And if you take the ratio of those, the x and y, right? Because x and y are identical, that ratio should be -1. So anyway, all right. What do y'all think? We have a way to find the slope of the tangent line on a curve that is not a function by using this implicit differentiation. All right, let me write our next one down here. X cubed plus x cosine y equals x plus y squared. Okay. We've already conceded that we are not even going to try to solve for x or y here. We're just going to do implicit differentiation, and we're going to be done. So I'm going to ask you to find again here dy dx. So that means I'm going to take derivative with respect to what? 2x on both sides of the equation. The left side is a sum of two things, right? So I can break it up into two derivatives. The right side is also a sum of two terms, so I can break it up. Like that. All right, what is the derivative of x cubed with respect to x?
3x squared.
3x squared. And you don't need that little chain rule, because you know if you did the chain rule, what would pop out on the side of it? A 1, right? A dx over dx. So I'm just going to say this is 3x squared. Is everybody sure that you understand why I'm just writing this? Anyone have a question? Okay. Yes. What about this next one? What is the derivative of cosine y with respect to x? Negative sine y. That should be pretty automatic. Times what? Ah, yes. Times dy dx. Now, why is that dy dx there? You don't like my towel. You don't like my mouse or my phone or anything, so I'm using my keys today. That better? Right? So I have the derivative of cosine of my keys should be negative sine of my keys, right here. Now we've done the derivative of cosine. I move inside, I take derivative of y. What's the derivative of y with respect to x? dy dx. So this has to be here. If you forget to do that, guess what? What you're solving for won't ever appear, and you'll never solve for it, and you'll be wrong, right? So this should pop out somewhere. Yeah? Okay. Equals. What's the derivative of x with respect to x? 1. Because that's really what? dx dx. dx over dx, that's 1. Plus, all right, what's the derivative of something squared? Something squared. 2 times that something. Chain rule times the derivative of what's down there. dy dx again, right? Dy dx again. So guess what? It's appeared twice. That's okay, but it's appeared. At least it's there, right? And now what we need to do is solve for it. We need to go get it by itself. So what I'll do is I will first just clean it up. I don't like that parentheses with the negative, so I'm just going to rewrite it as 3x squared minus sine y times dy dx equals the right side, which is 1 plus 2y dy dx. So how do you think I'm going to go about solving for dy dx here?
You guys split it in half.
Divide, I heard split it in half. I'm not sure what you mean by split it in half, though.
We put the 3x squared in the minus sine y.
Put that in parentheses? Oh, you mean like this? No, because that would mean you're actually factoring this out, right? Like if I put parentheses here, then if I wanted to, I could come back through and distribute it through, and that wasn't what you started with. So let me ask you this. Let's say I had this. 3x plus m equals 5m minus 5. If I asked you to solve for m, what would you do?
Isolate it.
You get it all your m's on one side, right? And you would get everything that didn't have m on the other side. That's exactly what I'm going to do right now. I'm going to grab every single term that has dy dx in it. That's this one and this one, right? I'm going to get those on one side of the equation. Everything that does not have dy dx on the other side. And which side you go to is up to you. Does not matter. I'm going to choose to take this entire thing and move it to that side because it was negative here. And when I move it to the right, it'll become positive. And that means my dy dx's are going to be on the right side. This one does not have a dy dx, so I'm going to move it to the other side like that. Understand? So I'm like adding and subtracting on both sides. So what is my new left side going to be?
3x squared minus 1.
3x squared minus 1. And then the new right side will be
2y dy dx over dx.
2y dy dx plus sine y times dy dx. Now, that's good. At least they're both on the same side. Now what?
Now we can factor it out.
You can factor it out. Perfect. They both have dy dx, right? Factor it out. So you get 3x squared minus 1. You didn't know you could factor out a derivative like that, did you? 2y plus sine y. So that's what would happen if I take this and pull that out. And just double check if you distribute that back through, right? You would get back this.
Now we can put all on divided, right?
Now divide both sides by that big ugly thing in parentheses. I'm going to take everything I see here, 2y plus sine y, divide it out on this side, and this entire side by 2y plus sine y. It'll go away here, and I'll have dy dx, which is what I wanted. So dy dx equals 3x squared minus 1 divided by 2y plus sine y. Done. And hey, it's telling us in order for you to be able to determine the slope of that tangent line, right? You're going to have to provide me with the x value and the y value of the point you're talking about. You do that, I give you the slope. All right. There's not many things that are going to be more exciting in the next 72 hours for you than this, okay? I'm telling you, this is a highlight of your weekend probably. All right, let's try something else. Let's try that last one. Cosine xy equals 1 minus sine y. Remember we looked at the graph of this, right? It was real weird looking? Okay. Can I come up with a formula for the slopes of the tangent lines?
Yeah, I was just curious. So with the xy, before the
That's not a constant. That's x times y.
Chain rule or
Yeah.
product rule inside of.
Yes, yes, yeah. So let's take a look. I'm going to take the derivative on both. Oh, find dy dx. Okay? So I'm going to take derivative with respect to x of cosine of xy. And that must equal the derivative with respect to x of 1 minus sine y. On the left side, I only have one term, right? So I've just got to take derivative of it. And,
But it's taking the derivative of both x and y.
well, yeah, what are you going to do here? This is where you have to be careful. What you see there is composition, hopefully. You have an outer layer, which is cosine. Inside that layer, you see a product. I hope you do. Yes? X times y? Okay, so chain rule, you have to start with the outer layer. What is the derivative with respect to x of cosine of something? Negative sine of that something, right? So I'm going to say that this is negative sine of the something was x times y, right? Now times, right? Times the derivative of what was in there. So let me write that down over here. This is what was in there, right? I need to take its derivative, but it's a product. Derivative of the first one times the second, plus the derivative of the second one times the first one, right? So I'm going to put that, since it's two terms, right? Product rule turns into two terms. I'm going to put a set of parentheses here. I'm going to say derivative with respect to x of the first one times the second one, plus the derivative with respect to x of the second one times the first one. Do you all see that? There's your product rule. Yeah, it's just I didn't take the derivatives. I'm just showing you. We had derivative of cosine of something was negative sine of that something times, because of chain rule, derivative of what was inside, which is a product rule, which is derivative of the first one times the second one plus the derivative of the second one times the first one. But it's a derivative with respect to x on all of these.
And then that equals.
Equals, now the derivative of this, let me see if you can do it. Do I need to write out like separate ones, or can we just do each one? Just do it. What's the derivative with respect to x of 1? 0. Okay, so it's gone. What's the derivative with respect to x of negative sine of y? Negative cosine of y. Are we done? No. Times what was inside of the sine. What's the derivative of what was inside of the sine? dy dx. I hope you see why chain rule is so important, right? You can't do this if you don't understand chain rule. You can't, it's not going to happen. Yeah, let's clean it up. All right, let's take some derivatives. What's the derivative of x with respect to x? 1. So this is just going to be 1 times y, which is y, plus, what's the derivative of y with respect to x? dy dx. Hey, that's the thing I'm looking for. Times x still, right? Times x. Close parentheses, equals, over here, negative cosine y times dy dx. All right. On your exam, I'll be looking at that as being a major part of accomplishing the derivative. Now, it's just the solving part left now, right? Just get the dy dx by itself. Now I see 2 of them, right? So I need them both on the same side. So can I just move this one over? No. Not yet, right? Because it's trapped in the parentheses. So I have to distribute this through to each one of those first, and then I can release it and move it to the other side. Or move the other one to the left. It doesn't matter. I'm going to do this distribution. So notice when I do this entire thing times y, the y doesn't go in here, get squared, right? It just sits out in front. So I'm just going to put minus y sine of xy. Okay, that's my first pass through with that. And then here to here, all that stuff does not go inside the sign, just going to be out front. I'll write it this way. Negative dy dx times x times sine of xy. And the negative sign I already took care of, right, by changing it to a minus there?
Where'd you get the x sign x? Oh,
No, I'm taking this and multiplying it through to here. So I had an x, right, times sine xy. And then I have dy dx. So I have x sine xy, I have dy dx, and it's minus because a negative times a positive is negative. Equals negative cosine y times dy dx. I guess you want to move everything to the right? All the dy dx is to the right? I think that's what I feel like doing. Any questions, though, before I erase this bottom part? When I move this to the right side, it becomes plus. So I'm going to put it in front of this because this one's a minus. It's just my personal preference. I don't need all these dots everywhere. It's implied multiplication, but I do them just to stress like this is not being multiplied inside with the cosine. It's separate. You could put parentheses on this y to kind of really stress that the argument is just the y, not the y dx. Now what? Factor out dy dx on this right side. I will be left with what? X sine xy minus cosine y. And once you get to that point, you're there because you're just going to divide that big thing in parentheses on both sides. Once you do that, you're done. And with equations, it doesn't matter which way you write them. So I'm going to write dy dx, and then I'm going to write negative y sine xy over this big ugly thing that I divided through by x sine xy minus cosine y. There it is. And as expected, to know the derivative, the slope of tangent line on that big ugly, well, it was actually kind of not ugly, right? It was a semi-attractive looking graph, right? If I want to know the slope of tangent line somewhere on there, you're going to have to give me an x and a y, and then I'll have to plug it into this, and I'll tell you what the slope is. What was the question?
Just a question of notation. Is
Yes.
it right to still, is it okay if you wrote the answer with y prime equals that?
You could write the answer as y prime. Yes, you could. But let me try to show you now. What I want to do is I want to go back to the first problem we did. I want to show you something, then we'll readdress that, okay? So let's go back to the first problem that I gave you, which was x squared plus y squared equals 16, right? And I had asked you to find dy dx, right? I said find dy dx. And we did it. But this time, what I'm going to do is I'm going to ask you to find dx dy. That means I want you to act as if y is the independent variable this time, and x is dependent on y. So how would things change? I would write the equation down. I would take the derivative on both sides, right? But with respect to y, right? So remember the language I'm using? Taking derivative with respect to y this time of x squared plus y squared equals the derivative with respect to y of the 16. And the derivative on the right side is the easier one, right?
Yeah.
That's a 0. But here's where we have some differences. Oh, let me split it up. D dy of x squared plus derivative with respect to y of y squared. So how is this going to be different?
Because your x is going to be the one that gets the
That's right. The x is going to be the one that we have to do the chain rule on. The 2x comes out, right? I mean, the 2 comes out, so we get 2x. But then we have to take derivative of the x itself, but with respect to y. So it's not 1. It's dx dy, right? Dx dy. And hey, that's what I'm trying to find. And I'm done there. Now this one, this time you will get the 1 to pop out. The 2 drops first, right? 2y, but when you take the derivative of y, the inside, right? With respect to y, dy dy is 1. And so you don't have, do you see that? Yes? Do you want me to write dy dy there? If you need to, go ahead. And if we solve, I'm just going to trust that you could move things around. You would move this over, right? And then you divide through. You should get negative y over x. Where? To this? I moved this 2y over, which made it negative 2y. And then I divided by 2x. And the 2's canceled, and I had a negative there. So, yes?
And the dy over dy just became 1. So
That's right.
took it out, right?
That's right.
I thought the dy basically just because you did the chain rule.
I did the chain rule. Right here. I did something to the second power, 2 comes out, times that to the first power. Times the derivative of what was down there, dy with respect to what though? Y. So dy dy, that's your 1. See, they switched places, didn't they? In the previous, when I said find dy dx, we had this one just was 2x. And now that I'm asking for dx dy, this one is just 2y, but this one's no longer just 2x, it's 2x dx dy. Got it? Are you sure? You're going to need this for 2.7.
Wait, explain that again just one more.
Well, which part?
With the dx dy, I think I'm just getting lost in the dx dy part.
Where is this coming from?
Yeah.
Okay, so look at this x squared, right?
Yeah.
X squared is really like something squared, right?
Yeah.
How do we take derivative of something squared? 2 times the something, right? Now to the first power, times the derivative of what's here, right? The derivative of what was in this box. So when I do 2x to the first power, now I need to take the derivative, right? I need to take derivative of this piece. But with respect to what variable? Y. So the derivative of x with respect to y is the derivative of x with respect to y. It's actually a good question. That's what we want to know. What is it? Well, it turns out to be this. But this right here comes from the fact that I'm differentiating with respect to a variable that is different than the variable that appears here. If they're the same variables, then it's just a 1. Okay? Yes, you sure? All right. All right. So now I'm going to try not to confuse you. I'm going to leave that right there. We know that that equation draws a circle, right? Draws a circle. So let's say I'm about to start drawing the circle, okay? Over here, I'm going to make a t-table. But actually, it's going to be a double t-table. Here's x, here's y, and over here, I'm going to act like there's time. T for time. At time 0, I would like us to go out to 4, 0 on the graph, which would be right, here's 4, right there. And then I'm going to start the watch. Ready? I'm going to start the clock, it starts turning, you know, the seconds start going by, and I'm going to start drawing the circle. Okay, so as I draw, right, I draw the circle. As I draw it, I might like speed up and slow down. It just depends on how I want to draw it. Then couldn't you say that the x depends on time and the y also depends on time? Where you are on the